seems. Let's see. So this chapter is alcohols and ethers. And what we're going to find is that for most of the chemical reactions, except for one, they're pretty much all dealing with alcohols. Ethers tend to be not terribly reactive. They don't do very much of interest. They are the occasional product of a reaction, but we don't tend to use them for much. In fact, they're so non-reactive that we tend to use ethers for solvents in a lot of organic chemistry reactions because it's not as polar as water and it's not as non-polar as, you know, a straight up alkane, and so it's a good mix of the two for some reactions to do in. And there's also a lot of reactions, and we won't ever get into this stage in chemistry, but where water is an absolute no-no in the reaction, or the reaction doesn't occur with water, in which case ether is usually the, or types of ether, not specifically ether, because is useful for doing chemical reactions. So we're going to divide up the chemical reactions into a series of different types of reactions. Each one we're going to have probably a slightly different approach to. If you remember those reaction study guide sheets for last chapter, there are those now already up there, I think, from last semester for the reactions in this chapter. So while we're doing this, and then certainly while you're going through your homework and stuff, start asking yourself those questions of, how am I going to recognize this reaction? How am I going to remember what to do in this reaction? What am I likely to get it mixed up with? And, you know, if you have that approach to when you're doing your homework and doing some practice, then you'll be ready for the test. So the first thing we have to cover real quick is one little tidbit that we didn't quite finish off with yesterday, and that's the difference between a primary, secondary, and tertiary alcohols. So primary alcohol is simply an alcohol that's on the end of a molecule. A secondary alcohol is kind of in the middle of a molecule. And a tertiary alcohol, you actually have to have another methyl group on there to do it. And so really what it is it's the number of R groups attached. So if I've got R, or here, let's draw it this way. If I've got an R group, a carbon, can't draw this morning, not good, R, C, OH, and then I've got two H's on that carbon, versus if that carbon has two R groups and only one hydrogen, versus if there's three R groups on that carbon and an OH group. So really, primary, secondary, and tertiary are kind of telling us the number of carbon chains on that molecule. And so what we're going to find is that depending upon where the OH is in the molecule, it's going to react differently for most reactions. And so even though we might only have 2 or 3 different types of reactions because we have primary, secondary, and tertiary alcohols, it might be more like 9 or 12 reactions because we have to multiply everything by 3. But the first part of sort of mastering all of that is simply knowing the difference between primary, secondary, and I guess I forgot an arrow, tertiary. So our first series of reactions are going to be oxidations. How do I recognize an oxidation reaction? Yeah, it has an O on the arrow. And then there are other arrows, right? But those are usually specific to a named reaction. And so what we're going to see is that when we do these reactions, I'm going to cover the generic oxidation and reduction reactions at the beginning, and then I'm going to save the named reactions for the end, but realize it's the exact same thing happening. The only thing that I'm adding when I cover the named versions of most of these is simply a color change that's associated with it, or something different written on the arrow. What? Yeah, so other arrows are specific to named reactions generally that have a color change or a precipitate associated with them. Meaning they're still oxidations. What happens to the actual molecule is the same in both sets of reactions. We just have to remember the extra step of what happens to the ingredients or what color change occurs in the reaction. So I'm going to put up a little grid that's sort of a summary of what we're going to talk about for the next several reactions. So if I've got a primary alcohol, I oxidize that to get an aldehyde plus water. And if I keep oxidizing it, then I can get a carboxylic acid. So that's one series of reactions that we're going to look at. And the idea is that for every primary one, we can also do something for the secondary. And what changes is that instead of making an aldehyde, I'm going to make a ketone plus water. And we'll find that if I try to oxidize a ketone, I can't. And so we're going to have a series of no reactions for some of these things. What's what? Ca is carboxylic acid. Yeah, that's one of those abbreviations that, you know, after a while, I just use it all the time. It's not California. Is that Ca though? California? And C little a would be calcium. So secondary ones turn into ketones, and then they can't react any further. We'll see why when we go and show some detailed pictures. And then for tertiary ones, they're kind of the bonus one. They simply can't be oxidized, at least not easily. Certainly we can oxidize just about anything by burning it, but like for instance when you were in lab, did you notice the tertiary alcohol didn't burn too well? Probably left a lot of carbon behind in complete combustion. Okay, so let's take a look at that first line. And then what I want you to pay attention to is the trends, because if you can know the first line, then the second line kind of follows suit, and you don't have to think about it as hard. And then the third line, I don't know, there's only one thing you can do is remember no reaction. If you really tried to oxidize it, if you followed the procedure to oxidize a tertiary one, you'd notice immediately that there is too many bonds on the carbon. So we've got primary alcohol, and we're going to oxidize it to get an aldehyde plus H2O. And I'm going to take that aldehyde, and I'm going to oxidize it further to get a carboxylic acid. So here's an example of a primary alcohol. And again, I'm going to oxidize it. And the way I like to think about oxidation reduction reactions is sometimes something else is going on in the reaction. So in this case, for the very first step, we can also think about this as being an elimination. So I'm going to put that kind of in red. And what I recommend is, well, there's kind of two ways to go through this. You can just memorize that an alcohol gets turned into an aldehyde plus water. And you should be able to figure out, you know, from knowing the structure of an aldehyde what to draw. Or you can recognize the mechanism, and if you focus on the mechanisms, then you just have to know what to do in each circumstance, and it won't confuse you if the molecule changes a little. So what we're really eliminating here is I've got a hydrogen here, so I'm going to eliminate two hydrogens, right? What happens if I eliminate two hydrogens? What happened in all of our other elimination reactions? You're right, kind of on the plus H2 part, but we made a double bond, right? And so notice in this case I'm making a double bond between this carbon and that oxygen, right? And in a lot of reactions we really do get H2 gas. Since these are generally done in aqueous conditions, we actually get plus H2O from that. And so what I like to think about is that O in the oxidation means that I've got lots of extra oxygen around, and so I can make water. So if you think about this as simply being an elimination and making carbon-oxygen double bond plus the H2O, it's a pretty easy way to remember that it's an aldehyde plus water. Or honestly, if you can remember that an alcohol goes to an aldehyde and you simply change the OH to a double bond to O, that's one way to do it too. That actually, arguably that's the easiest way if you can remember that primary alcohols get turned to aldehydes. If you remember that the first step in the oxidation is elimination, gets you the same route. Gives you a little bit of better understanding. It also explains why the water is there too, right? And then if I oxidize that further, then I get a carboxylic acid, and this step is complicated. So there's no real good way to kind of show it. Reacting. If you want to think about it, and boy, is, remember, there's still a hydrogen here in my aldehyde, right? And so I'm kind of adding this back in there. So I'm adding another bond to oxygen. Like I said, oxidation reduction reactions, the mechanisms are even more complicated than what I'm showing you. And yeah, I noticed the little yellow box showed up, of course. Oop, there it disappeared. They're complicated, and even the explanations that I'm giving you are kind of simplified and watered down. I'll be honest, I'm not sure I remember the much more complicated explanations for most of these oxidation reduction reactions. So, alcohol to aldehyde to carboxylic acid. You guys want another example? Yeah. One thing I want you to start to recognize is if you know how to do one reaction, you know how to do them all. Because the only thing that I can do to change this reaction up is maybe I'll put the HO on this side and I'll add a methyl group. That's the only thing I can do to make it harder, right? I'm not going to add new functional groups. I'm not going to add carbon-carbon double bonds. The only thing that changes is that R group. And so if we kind of take a look at what's happening, then, you know, I just draw my molecule as it is, and I have to make this an aldehyde plus my H2O. So once you get the pattern, the nice thing about organic chemistry is that it's always the same. Meaning, if you know how to do a primary alcohol and it's got 2 carbons, then you know how to do it with 3, 4, 5, 10, 100, 1,000. Well, okay, you know, let's not get ridiculous. And then we'd change that same thing to a carboxylic acid. Now, remember when you're doing things on the website that sometimes it'll flip the molecules around, it'll rearrange them. And so if between a step the OH moves from the left-hand side of the molecule to the right-hand side of the molecule, did it really move there? No, we just flipped the molecule around, right? So you do have to have some flexibility when you're looking through those things because the computer likes to swap them around. Okay, secondary alcohols are exactly the same way for the first step. And the only thing that changes is that because a secondary alcohol is in the middle of a molecule, it makes the carbon-carbon double bond in the middle of the molecule. And instead of calling it an aldehyde, we call it a ketone. And so one of the things you're going to learn to recognize, especially in the next chapter, which is aldehydes and ketones, is that the only difference between an aldehyde and a ketone, at least structurally, is that one is at the end of the molecule and one is in the middle. So for a secondary alcohol, I have to have an OH group in the middle. And again, we can kind of think about it as the same sort of reaction in that, you know, I've got that hydrogen there. I'm eliminating that. And so now I get a double bond double bond oxygen, but that's in the middle of the molecule now. And I get plus H2O. So really the only difference between the primary and the secondary version of this reaction is where the double bond is, right? It's either formed at the end of the molecule because it's a primary alcohol or in the middle of the molecule because it's a secondary. And then notice that I've got 4 bonds here, right? Therefore it's impossible, I won't say impossible, therefore it's hard to oxidize because we can't gain bonds to oxygen. Without breaking the bonds to carbon. And carbon-carbon bonds are pretty robust. We don't tend to break them except in extremes. And in fact, at this point, if you break that carbon-carbon bond, well, now you've got a carbon with nothing else attached to it but some hydrogens. It basically gets turned into CO2. At this point, if you wanted to further oxidize this molecule, you're essentially combusting it, meaning you're going to have to burn it up or break it up entirely. And so that's why there's a no reaction. There's just too many bonds to carbon already, and nothing can happen.
There's 4 bonds for the primary.
No, if you look, one of these bonds here is to hydrogen, right? So when I say 4 bonds, I mean 4 bonds to carbon or hydrogen, meaning there's no carbon-hydrogen bond is what I'm trying to say. So if you look at this step for a primary alcohol, there's still a bond to hydrogen that's pretty easy to break. And if you look at the secondary one, since there's 4 bonds here, 1, 2, 3, 4, there's no bond to hydrogen to break. So I kind of phrased that poorly. And if you take a look at it, then you can certainly see why a tertiary alcohol can't react or can't be oxidized. If the first step in that oxidation is an elimination, is there any hydrogens to eliminate on that carbon? Yeah, it's got bonds to 3 carbons. Therefore, hard to oxidize. And even if I said, okay, fine, I'm not going to remove it and make a double bond to oxygen, is there any way I can just simply bond to make another single bond to oxygen? Not really. And so tertiary alcohols, because there's no carbon-hydrogen bonds, means there's no way that they can be oxidized. There's no way to break bonds to hydrogen, which is the other half of oxidation reduction, right? Meaning oxidation, gain bonds to oxygen, lose bonds to hydrogen. Well, in this case, there's no way to lose a bond to hydrogen on that carbon atom. So for me, the best way to remember that set of reactions, I like the words. I mean, I remember primary alcohol goes to aldehyde plus water. That's pretty easy, not too hard. I know what an alcohol is. I know what an aldehyde is. It's not hard to change from an OH group to a carbon double bonded to oxygen. So for the oxidations, because the mechanisms are a little tricky, sometimes it's best just to remember the words. But what works for you is what you should do. That being said, I like to have that idea of the understanding of the mechanism because that reminds me of why tertiary alcohols can't be oxidized at all. Secondary ones can only be oxidized to ketones, and then ketones can't be oxidized, right? Okay, second set of reactions, and this is maybe one of my favorites, dehydration. This is one that we're going to see coming back over and over and over again, especially in the biochemistry chapters, because your body loves to both remove water from things and add water to things. I should also point out that the oxidation reduction reactions are also a lot in the biochemistry chapters simply because those are usually the energy intensive steps in a lot of different chemical reactions. That's where your body gets energy from, is by oxidizing molecules, or by it gets the energy by oxidizing the molecules. It can store energy by reducing molecules. So dehydration means what? Yeah, loss of water, right? Meaning removing water. We should be careful. There is a reaction called dehydrogenation, which is removing hydrogen, and that's pretty easy to sometimes get mixed up with dehydration because there's a lot of dehyde in both of them. So again, we're going to have a series of reactions for primary, secondary, and tertiary. And for dehydration reactions, a lot of times I've standardized on simply minus H2O above the arrow. But occasionally, you'll see them as simply just a strong acid and heat. So H2SO4 and heat. So obviously, the one with a minus H2O on the arrow is pretty hard to not figure out that that's a dehydration, right? The one with the sulfuric acid and heat, that's a little tougher. If I remember right, and I'm only going by memory, I'd have to look. At least on the practice and on the test, I tend to only put the minus H2O arrow on. That being said, be careful, and occasionally if you see H2SO4 and heat, know what's happening. So here, I'm going to have a primary alcohol, and this is one of those little weird parts. It's actually a primary alcohol plus a primary alcohol. And it gets dehydrated to form an ether plus H2O. And the tricky thing we have to remember about this is that there are multiple products if the two primary alcohols are different. So we're not quite done with multiple products in our answers, but most of the rest of the reactions, there's usually a single answer that we're going to get. What we're going to see is that secondary alcohols get dehydrated to form alkenes plus H2O, and then tertiary alcohols are dehydrated to form alkenes plus H2O. Wait, yeah. So in this case, you know, they behave the same, so you kind of get a sort of a break. And then maybe, I guess, if we're putting notes here, we should also remember that we sometimes have to use Zaitsev's rule, because really, what are dehydrations if I'm removing a molecule from something? They're really just elimination reactions, right? Elimination. If I'm removing water from the molecule, that's an elimination reaction, isn't it? And so really, this is kind of a repeat of something we've already seen. It's just that we're going to be removing a water molecule instead of, say, hydrogen or HCl, which is what we did in the first test. So let's take a look at each of these closer. Primary alcohol plus a primary alcohol is dehydrated to form an ether plus H2O. I should also note that by process of elimination, since it's minus H2O, that means that we have to have plus H2O on the product side, right? A lot of people will sometimes forget things like that. Or a lot of these reactions, a lot of these reactions have plus H2O on them, and a lot of them don't have plus H2O, so people get confused. So that's where the mechanism can help you determine it, and that's where, you know, a little bit of common sense. If I'm losing water from the molecule, it better show up on the product side. So if I've got a primary alcohol plus a primary alcohol, and notice here I made them symmetrical, I made them the same. We're going to lose water by taking an OH from one molecule and just the hydrogen from the other. So the key on dehydration reactions is always locating that water. And then the other half of the reaction is you have to figure out what bond was broken. So if I break the bond between that oxygen and that carbon, then I've got a lone electron there. But if I break the bond between the OH group here, then that electron is on that oxygen, right? So the idea is that when I'm eliminating things, those parts go together. So that electron that was there is going to pair up with the electron on that water, and that's what's making that new bond there, right? So this new bond here is due to the free radicals combining together. So new bond between free radicals. And then I guess, of course, plus H2O, because that's what I removed. So the other thing that you're going to notice I'm starting to show a lot more, especially if we want to put together pieces, is what's really happening to the electrons. Meaning, if I'm breaking that bond, I'm really, you know, getting an electron on the H and the OH part too, but that should be pretty obvious that the H and the OH go together to make water, right? I guess instead of writing the water that way, I could emphasize that, and that's also from the free radicals. So what this really says, as far as reactions go, that for dehydration reactions in general, water is a small stable molecule. It's very easy to remove from more complex molecules. Okay, so that's with symmetrical molecules. And so notice that led to one product. But if I make it unsymmetrical, then I can get a variety of products. Because really, if I write this reaction down, I don't have to show alcohol plus alcohol. If I just show a single primary alcohol, there's always more than one of those around, right? Meaning that on the test, you might see the reaction simply like this. And it's up to you to realize that there's really lots of these, right? And so you have to realize that, you know, it's going to make that same part plus H2O, because we can add in a second copy if we need it, right? Does that kind of make sense? that there's always more than one of everything around. So let's do it with an unsymmetrical example. Unsymmetrical. So there's that plus that. And I'm going to label them just to make it easier. So I've got basically molecule A and alcohol B. And remember, there's bajillions of these, right? Because we know that even in a small quantity of reactants, we've got millions and billions and trillions of molecules in there, right? And so there's lots of A's and lots of B's all floating around. And so when we start to dehydrate them, we can get a variety of combinations, meaning that if that molecule, instead of reacting with the B molecule, reacts with a second A molecule, then that's the reaction we've already seen, right? So this is A and A reacting, right? If B reacts with a molecule that looks exactly the same as B, like this, then notice that we're going to get a molecule that has both parts are B. So this is B and B. And then notice that I can also react A and B. So if the real reaction as it's written, A and B react together, then I get something like this. This is AB. And so I get three products here, and then of course plus my H2O. And so the reason we get multiple products is because we have the reactants can react with either themselves or each other. Does that make sense? Yes, no? I mean, I know, I got to be honest, going through it the first time, it's not going to make 100% sense. What I'd recommend is, you know, do the homework, check your notes, do that iterative process, and then when you're done with it, sit down and say, how am I going to remember everything? Print out those study sheets if you want. Maybe I'll even remember to print them off for lab tomorrow, and start filling those out, and then practice this. Oh, I should also point out, one of the things I programmed last night that I'll have to go in and fix and do for this new chapter is, for some reactions, you know how we always said that I can't make the computer circle the right answer or the most favored product? I figured out how to do that yesterday afternoon and late into last night. So it's a little late for the first two tests, but for the next test, you know, we can do it on. Okay, so if I have symmetrical products, how many, or symmetrical reactants, I get one product, right? If I have unsymmetrical products, I get three or more, right? Three, really, in this case. Okay, if I do a secondary alcohol, this is kind of going back to more stuff we're familiar with. And maybe I should add one more word. We're going to go back 2 slides and add the words. Let's see. This is an, 3 slides, I guess. If it's a primary alcohol, and this sort of elimination, we consider this intermolecular, right? Because it's between 2 molecules. Whereas in these cases, we're going to see that it's intramolecular, meaning it occurs in the molecule, meaning there's not a second molecule. So maybe one way you can remember the difference of what happens here is intermolecular versus intramolecular. Do you really need me to actually show you where I wrote intermolecular and intramolecular?
Yeah.
Okay. Okay. Remember, these are all also taped and on the internet. How many people have gone back and watched any of them? Taylor's the only one that sits and watches them late at night and then scares the shit out of herself. They actually use these as a form of torture with the CIA. They make me send them the tapes, and then for suspected terrorists and stuff like that, they lock them in a small room and just play this over and over and over again. It's pure torture, I tell you. Okay, so we got a secondary alcohol. It's going to be dehydrated to form an alkene plus water. So here's my secondary alcohol, right? And remember, we just said that this is our standard elimination reaction. So I'm going to lose this OH, and I'm going to lose either the H on the right side or the H on the left side to make that carbon-carbon double bond, right? That's the same elimination that we had when we were doing the other reactions. And so here, in this case, because my molecule is symmetrical, I just get one carbon-carbon double bond plus H2O. And remember, kind of the middle part that we're thinking about is that when I break that bond, I get an OH like this, and I break this bond, and I get an H. And remember, those electrons are forming that carbon-carbon double bond. And so if you kind of think about it in terms of mechanisms, maybe that helps you see where everything is going. And then, of course, the water radicals go back together. So remember, every one of these reactions can be thought of in different ways. You can memorize the words. I had one girl, that's how she did it. She had literally just flashcards with words, and she would turn, and she knew what a secondary alcohol looked like, and she knew how to turn it into an alkene. I've had people remember the mechanisms. I've had people just break things apart into free radicals always. You have to figure out what works best for you for each reaction. And in the end, only practice is going to work. So we've got that sort of reaction. And then where it goes different is if I have something like this, where I have an unsymmetrical molecule. So notice that this was symmetrical. This is unsymmetrical. And so in this case, I can lose that hydrogen, or I can lose that hydrogen. And so I get two different products, depending upon which one is lost. And then what do we know is the favored one in this case? Yeah, so this is Saitsev. He said, when eliminating, make sure to wipe. Now, when eliminating, remove the hydrogen from the carbon with the least hydrogens. And so Saitsev says that this hydrogen is easier to remove and more stable. And it really is simply saying that a secondary carbocation, well, we won't worry about that. We'll just leave it like that. So we can get multiple products if we have multiple places for it to be removed. Because remember, this is symmetrical, meaning that this is the same as that. So we have to remember, if it's symmetrical, we tend to only get one product. If things are unsymmetrical, then we tend to get multiple products. And we can do the same thing for a tertiary. It's the same reaction. It's just that we have more carbons around. How many different products can I make from this, since it's very unsymmetrical? Yeah, see, I can remove this hydrogen, right? I can remove this hydrogen, and I can remove that hydrogen. And so I can actually make 3 different places for the double bond, because I made a very unsymmetrical molecule. And of course, plus H2O. So I can put the double bond here, here, or here. And I'll give you a second to draw those. I know I'm speedy at the drawings because, well, I draw them a lot. think one of the reasons I've decided chemistry is tough is, and I think biology and those classes are too, but ask yourself how many new things you're learning today. And then go and sit in your sociology, psychology, or some other class and ask yourself how much you're learning. Or compare how much you're learning in A&P or in some other class. Owen, how's it going today? You look like you're about to fall asleep or something. Okay, so which of those is favored by Saitsef? So Saitsef says these are good. And so what I'll do is I'll actually go through those hopefully this afternoon, since I should have some time off, and I'll go and I'll fix up and make this quiz start circling all the favored products now. That should help you guys out, I hope. Even if it's boring and tedious for me. Okay, so that's dehydrations. There's one special dehydration that gets its own name, but it's still a dehydration. It's called an esterification. And for some reason, every time I say esterification, it reminds me of a bunny rabbit hopping down a trail because I think of Easter for some reason. I don't know. It has some uniquenesses to it. It uses this set of reaction arrows. And what this means is, remember, the double arrows mean equilibrium. And which means that the reaction can technically go in either direction. And in fact, what we're going to realize is that since this is the chapter on primary alcohol or on alcohols, we're going to run it in the forward direction, and then we'll see this exact same reaction in the carboxylic acid chapter in both the forward and backwards directions. So this is one of those that we get to see over and over again. And then the H plus simply means that it has to be done under acidic conditions. And so for this reaction, it's a primary alcohol plus a carboxylic acid. We're going to see the double arrows to help us remember it can go both ways. Whoops, not oxidation, H plus. And we make an ester, which is why it's called an esterification, plus H2O. So not the next chapter, that's aldehydes and ketones, but the chapter after that is on carboxylic acids and esters. And by the time we get to carboxylic acids and esters, since we've been drawing them so much, you'll probably recognize them pretty easily. So here's my alcohol. Here's my carboxylic acid. And this is a reaction that I want you to kind of pay attention to the mechanism for. Otherwise, it's very easy to get screwed up what's happening. Oops, make that double bond oxygen better. So what do we remember about dehydration reactions? We're losing water, right? So where's the water in these molecules? I'm going to ask that question lots and lots and lots in the next couple chapters because dehydration reactions occur lots. So if you get good at finding water, you will. Yeah, so you've got an OH here and an H here. And it doesn't matter if you switched which OH and H you took, because the reaction is going to occur the same. There really is a one that's favored, and I never remember which one it is. You can do an experiment to prove that the OH always comes from one or the other molecule, and I never remember which one. And so notice that I'm breaking it apart here, and then I'm breaking it apart between that oxygen bonds. And so when I put it all together, what I'm going to get is that. And notice I'm going to flip the carboxylic acid around so that it looks like that. So notice that this is coming from the alcohol. That part is coming from the carboxylic acid. So it's very important because you can see them drawn either way, meaning that I can also draw the reactants like, or the reaction like this, and that's the same. And so notice there's only one product. I just flipped it. That's a retarded one. There. What I'm trying to get at is that when you do these reactions on paper, what you're going to find is that sometimes the alcohol's on the left, Sometimes the carboxylic acid's on the left. Sometimes the computer program draws it carboxylic acid side, alcohol side. Sometimes the computer draws it alcohol side, carboxylic acid side. So these molecules can be flipped around, turned upside down, turned inside out, rotated all around, and you have to be able to follow what happens. And so, notice that on the side that has the carbon-carbon double bond, that's considered the carboxylic acid side. So if I kind of divide the molecule apart, that came from the carboxylic acid, that came from the alcohol. Same thing up here. So if my carboxylic acid has 4 carbons, then that means that attached to that carbon double bond has to be 4 carbons, right? So don't let it get it confused how it's drawn. Be sleuthy, be paying attention, kind of look really hard at those molecules and say, okay, I know where things are coming from. Okay, so that's esterification. I put it as a separate thing in the study guide or that reaction guide, but really it's just a dehydration. It does have a different arrow, so a little bit more work maybe, but that's okay. Okay, so we can also have what's called alkaline hydrolysis. And that's where we take an alkyl halide plus a strong base, and we make it into an alcohol plus a salt. And what this really is simply a double displacement reaction. So if you remember double displacements, then you can kind of do it. And since it's a double displacement reaction, it also means it's really just a substitution reaction. Now, I have to admit, the reason I think it's kind of a toughie is that we're so used to doing oxidations and dehydrations that those are the majority of the reactions we see, that when this one pops up occasionally, we're like, what's going on? So if I take a look, an alkyl halide is anything that has a halogen on it, and a strong base is anything with an OH and a metal. Now, on the computer and when I draw things, 99.99% of the time my strong base is a sodium hydroxide, and 99% of the time my alkyl halide is something with a chlorine on it, right? But if you saw something with a bromine, and instead of NaOH you saw KOH, that should be kind of the same. So what we're really swapping is the chlorine and the OH group to give us that alcohol plus, in this case, literally salt. But when we say this, we really mean any ionic salt. Meaning, if it was a KOH, then we'd get KCl as our product. And kind of the way I remember this reaction is simply, there's nothing else much interesting that can happen with it, right? I guess I could try to stick the sodium on where the chlorine is and get, if I tried to swap something else, I could get maybe this. But what's weird about ClOH? Yeah, it's an anion and an anion, so that doesn't work. And so what you really have is you have that the alkane group is acting like a cation. There's my anion, cation, anion. So if you think about it as a double displacement reaction, we're simply swapping the cations, right? Meaning I'm putting the, oops, wait. Oh, I was confusing myself for a moment. I was looking down at this and I'm like, I just put the cation with the cation. What's going on? Remember, that's wrong, right? Yeah, I looked at that as the answer and I'm like, that doesn't really work. But no, I mean, we've got the cation, the R group, and the anion, the OH, and we just swap them. And with that simple, well, we'll go do that later. Okay, we've got 2 sets of named reactions to go through. You've already seen them, so you already know the answer to this to a certain extent, the Lucas test. What's the Lucas test good for? Yeah, primary, secondary, or tertiary, and how does that do it? Yeah, fast, super slow. At least we consider 30 minutes slow for most chemical reactions because no one wants to sit around that long. Jess, are you awake? I think you're just about out. So, what we're going to see is that we can think about this test as a dehydration reaction if we want. Dehydration. It's just that we're not going to see it written as a dehydration. Instead, the way we generally see it as is plus HCl, and then the zinc chloride is on the arrow. And the reason the zinc chloride is on the arrow is it's required for the reaction to occur, but isn't necessary, or doesn't take place, or doesn't show up on the product or the reactant side. So nothing will happen if you just add HCl unless you add the zinc chloride. So all of the reactions are the same, even though for whatever reason, I also have a bad page break on there, the timing is different. And so really, it's primary plus HCl goes to an alkyl chloride, and that alkyl chloride is solid plus H2O, and this is slow. And then everything else is exactly the same. It's just that this is medium, I guess, and that the tertiary oops, might have crashed my computer. Yep, looks like we crashed PowerPoint, so we'll reboot and we'll redraw that up there. I'm assured that in our new fancy building, we're going to get new fancy recording devices and everything else, so we won't have this problem. Anyone want to place bets on that? Yeah. So what had people gotten down by the time we quit? So really what I'm saying is it's primary, secondary, or tertiary plus HCl, zinc chloride, and I get an alkyl chloride plus H2O. And that alkyl chloride we want to note is a solid, because what's the way we tell if this reaction occurs or not? Precipitate, right? So what you need to know about the Lucas test is how to write the reaction, but you also need to know the visual clues that go along with it, and you need to know how it differentiates between primary, secondary, and tertiary. Fast, slow, medium, I guess. So let's just take a look at it. For simplicity's sake, we'll just draw a primary alcohol to start with, plus HCl. Now, I said that this is a kind of like a dehydration reaction, right? So what should you look for in a dehydration? So where's the water? Yeah, see, I've got an OH, right? And I've got an H here. And so that means that I'm breaking this here, and I'm breaking it at the Cl. So it's pretty easy to see how I get my alkyl halide, right, plus my H2O. And then we should note, and I don't think I actually write it down necessarily in the reactions, but that generally is a solid, that's our precipitate that's forming so that we can see it. So again, when you look at these reactions, if you want to remember that, you know, primary, secondary, tertiary alcohol gets turned into an alkyl chloride plus water, you can. I'd simply remember that if I see plus HCl and zinc chloride, that it's a dehydration, and use the mechanism to figure out what happens. Much easier. So everything that I can link and say, this a dehydration works for this, that's one less specific thing I have to remember, right? Because it's easier to remember dehydration than it is to remember all the other stuff. Jess, just checking. And then it doesn't matter if I use a primary, secondary, or tertiary. The same thing is happening. So here's an example of a tertiary. I guess we'll put that this is slow. And I think in the computer I actually write slow and fast next to the answers, because That's the part that you're supposed to remembering, right? Whether it's slow or fast. And so again, same thing. Find the water. Figure out where you break the bond. So that's on that carbon and that chlorine. Redraw the molecule hooking up the two parts. And don't forget the water. So really just a dehydration. And so maybe I should cover that when I covered dehydration reactions. For whatever reason, when I went through and made the guide the first time, I did the dehydration reactions and I saved all the name stuff to the end. Don't know why. So did you learn anything on this reaction? I don't know. See, that's up to you guys. If you can remember it's a dehydration, then it's just the same shit we were doing earlier. And if you remember from lab the fast and slow part, then you didn't learn anything new. That's okay. Same thing, this next reaction, you're not going to learn anything new if you're kind of paying attention in lab and you understand what an oxidation is. And that's the chromic acid test. This is one of my favorite ones. Who did the chromic acid test in lab? That's what I figured. Yeah, that's the one that makes all the pretty colors, so I think it's the neatest one. Yeah. So the chromic acid test is really an oxidation. And so that means that you have to remember our stuff from oxidations, meaning primary alcohols go to aldehydes, secondary alcohols go to ketones, and tertiary alcohols don't react. So there's nothing new there, meaning it follows the same normal rules as oxidation. The things that'll change are when we do the test, we have this rather crappy arrow because it's got lots of stuff on it. So it's got chromic acid and H2SO4, and quite often, sometimes you need to heat it. So the acid part is, of course, the H2SO4. The chromate part, or the potassium chromate, oops, I threw an extra R in there for some reason. Very strange. That's just K2. No krypton in. Why can't krypton be in that compound? Krypton is a noble gas, right? Doesn't react very much. So really, sorry, that's chromic, and then the H2SO4 part gives you the acid part. And so what we need to remember from that is that primary and secondaries react fast, right? With a color change. And the chromic acid is generally orange-ish. It can be very light orange, or if it gets so dark, it can almost appear red, but it's generally orangish, and it generally goes to a greenish blue, but it can also even be ugly brown, if I remember right from your reactions. But the idea is that it reacts fast, less than 5 seconds, so it's a nice, quick, and easy, dirty test. The bad thing is that it does not differentiate primary and secondary easily. Meaning you really can't tell the difference between a primary and a secondary alcohol in this reaction, since they both react very fast. And so when you do this reaction, what I want you to kind of focus on is that if I have, say, a primary alcohol, do I need to go back quick? Keep adding a chromine. Did you say yes or no? No class this Friday. If I'm really motivated, tomorrow morning I'll tape a lecture on aldehydes and ketones that's like 20 minutes long on how to name them, and you guys can consider that your lecture. I'll let you know by the afternoon.
You said for tomorrow? So we could have no class tomorrow? So you said there might be no class tomorrow?
I love how people miss all the words in between. There's no class on Friday.
So
I might tape a lecture and let you know on Thursday. But it'll be only like 20 minutes, and you can watch it anytime you want. So if you guys all want to get together and watch it in memory of me, you can. Okay, so primary alcohol goes to an aldehyde plus H2O. So this is exactly the same reaction that we would see in where we were just talking about the oxidation reactions. The only thing I want you to recognize is that this is going to be orangish red. This is blue-green, and that it's fast. So that's the additional part from the naming that we expect to see when you're writing a reaction. And I'll be honest, I'm not so sure I care if when you write this reaction, you write all that stuff down every time. But if I ask a question that simply says, what is the visual evidence of a positive chromic acid test, you better be able to tell me that it's from orangish to blue-green. Aldehyde. Sorry, ALD. Yeah, I abbreviate after a while. What's KET?
What? Ketone.
Yeah, see, I get lazy. I have to be honest. I do. And that if I have a secondary alcohol, that's going to go to a ketone plus H2O. And so really this is just review because we've already covered this. Ketones in the middle of the molecule plus H2O. And again, I want to see, or I want you guys to start getting that idea that it's orangish red, or maybe orange red we'll call it, and then blue-green, and that it's relatively fast. So for the named tests, what happens is in class we usually cover them a little bit, going how to go through them. They might appear on the homework, I don't remember, but they certainly show up in lab, and I expect you to know the stuff from lab for the actual test. And so when you're going through lab, every single time you do something, you should be asking yourself, does this meet my expectations? Meaning, did this secondary alcohol actually react really quickly and change colors? And if it doesn't, then you should be saying, well, Jay either labeled something wrong, I grabbed the wrong chemical, something's contaminated, or it just doesn't work for some reason, and you have to, we have to hunt it down. Okay, one last mini topic. This one is one of those things that something similar to it is going to crop up in the future. It's compounds or groups that actually have more than one property for acids and bases. So the idea is that alcohols, kind of like water, can behave as acids and bases. So for instance, you were doing the potassium permanganate test in lab, right? And that was the one where you had to take and separate it into 3 parts, right? You did one under acidic conditions, one under basic conditions, and one under neutral conditions, right? And so, what that's trying to say is that alcohols will react differently depending upon what conditions they're in. We're going to see that in the biochemistry chapter that, for instance, amino acids look different in acidic versus basic versus neutral pH solutions. And so we're going to see that again and do that. So here, if I take a look at it, here's my alcohol. And if I react it with water, then I can get an alcohol that's got 2 H's on it and a plus charge, plus an OH minus ion. And the idea is that this lone pair of electrons attracts the partial positive charge on the hydrogen of a water molecule. It's just like, for instance, so an aside, when we did this, that's an ugly looking H, but that's okay. When we were talking about acids and bases in chapter 15 last year, we said that we can get something like this. And we called this a hydronium ion. And that in general, we really write the water dissociation as simply HOH breaking apart into H plus OH minus. Even though we very rarely have simply a hydrogen ion floating around, it's usually associated with a corresponding water molecule. And then the second way that we can kind of think about it is that if I take that same OH molecule and I react it with sodium ions, then I can get something like this where the sodium and the H swap, and I get plus H2 gas. So here, oh, I'm sorry. I was like, yeah, we have to throw some 2's in to make it balanced. Now remember, we don't tend to balance these reactions very often, and so don't worry too much about balancing it. What's the only reaction that I ever make you balance in class? Combustion. By the way, I added that to it too, so now it actually shows you what the balancing is to it. And there was no combustion practice, so I added a bunch of combustion practice, or at least I added 2, and I just have to type in the rest. Meaning the hard work is figuring out how to make the program practice, or put the practice up there and make it work. The easy work is the easy and tedious work is adding more and more examples. What was your question? Yes. And that's where we'll end for today. Jess, did you stay up super late or something? Jasmine, were you on duty with her? Jasmine, were you on duty too?